All right, so here we're looking at the first problem for the end of the chapter 17 notes. It says the average ACT score is 28 with a standard deviation of 3.4. That's referring to the population. So it's saying that the true average SAT score is 28. So we'll go ahead and record that as our mu. So mu is equal to 28 and our standard deviation is 3.4. So it says I take a random sample of 150 students, so that number is my n. Then it asks what the probability is that the average score for these 150 students is greater than 29. So when I'm talking about an average from a sample of subjects, that's x bar. So x bar is 29, or greater than or equal to 29. But we'll get to that when we actually get down to the do step. So the difference here is, well, let's go ahead and check our conditions first. So we will check and state those three conditions for the central limit theorem. So the first is our subjects must be obtained through simple random sample. It says we take a random sample, so we consider that checked, stated, SRS, and we're good to move on. Number two, our sample size needs to be greater than or equal to 30, or the population is already normally distributed. Well, I don't know anything about the population distribution, but, and again, coming back to that last statement, I don't know anything about the population distribution. It might be skewed. It might be uniform. It might even be something like that. We got to play around with this on the applet on the computers. My population distribution might be some non-uniform, bimodal, skewed, whatever strange shape you could have created for that population distribution. What we saw was that as n is getting larger, the sampling distribution becomes approximately normal. And so that's where these steps come in. So I have to know that it was an SRS, well, I know that. And then I have to know that n is greater than or equal to 30, or that I started with a normal population. But thankfully, 150 is greater than 30, so that will be how we satisfy that second condition. So 150 is greater than or equal to 30. And now we want n to be big enough, but we don't want it to be too big. So I need n to stay under 10% of my population. So if n is 150, safe to say there are more than 1,500 students out there in existence. Okay, so we're good. Now that I've checked all three of these, the purpose for these conditions is so that I can apply the central limit theorem. The central limit theorem is what lets me say that no matter what my population distribution was, this mu and this standard deviation, my sampling distribution, so if I'm looking at a bunch of sample averages, will start to follow an approximately normal distribution. So each of these little X bars that I'm drawing is representing me going out and asking 150 students, what was your average ACT score? Another 150 students, what was your average ACT score? Another 150 students, what was your average? And I'm recording all of these. And the central limit theorem says that all of these sample averages will hover around the true average, which is 28. But maybe I collect a sample of 150 students, and I get a strange amount of AP students who likely did better on the ACT, so now that sample average is slightly above the true average. There's going to be some variation from sample to sample, but the majority will fall very close to that true average of 28. Well, what about our standard deviations? How many points for the ACT score do I have to go out to meet that structure we've seen for so many months now, where 3 standard deviations in either direction covers 99.7% of all observations? So that's where our formula comes in. So I know that this is going to follow a normal distribution, mu standard deviation divided by n. And so that's a sloppy n. Let me fix that. So it's my population standard deviation divided by, well, how large was my sample? Okay, so looking at all of those parameters I first listed up here, I'm now ready to start using this formula. So I know that this picture will be centered at 28, and then each of these tick marks, each of these standard deviations will, what size will those be? It's going to be 3.4 divided by the square root of 150. All right, and that turns out to be 20 and a standard deviation of 0.278. And you can check that on your calculator. Now this is where it's different, like we saw in that activity on the computers. When I'm conducting a sampling distribution, where I'm calculating a bunch of sample averages, there's going to be much less variability as my sample size increases. And so we can think back to the average height. The probability of finding a single person with an average height above 6'6", well, that's pretty small. But the chances of finding 30 people who have an average height of over 6'6", that would be almost unheard of to have if I had been following a simple random sample. So that's the idea. If I'm looking at a group of people, it's unlikely that their average strays that much from the true average. So larger sample size, less variation. Okay, so looking down here, we can add that to our picture. I'm just going to call this, we'll call it 0.27. Just bear with my picture because it might get a little sloppy. Okay, so we have 28 plus 0.27. That just gives us 28.27. Okay. Another standard deviation of 0.27, that's going to give us 28.54. Okay, plus another standard deviation of 0.27, that's going to give us 28.81. Okay, the problem wants us to find, let me go back to a normal sized line. The problem wants us to find the probability that my sample average of 150 students is greater than or equal to 29. Well, 29, that's more than 3 standard deviations away from my mean. So maybe you're making some predictions as to the size of that probability, but hopefully you're thinking it's going to be pretty small, since again 99.7% of the data will fall in between 3 standard deviations from the mean. Okay, and to find out just how small it is, we're going to use normal CDF. Our lower bound will be 29, that's where we wanted to start adding. And we're going to extend it on and on and on. And the center, the mean for this distribution is 28 with a standard deviation of 0.278. All right. So we find that the probability that I find 150 students who have a sample average of greater than 29 is 1.609 times 10 to the negative fourth power. So what that 10 to the negative fourth power is telling us, it's saying that that decimal needs to be moved 4 places. So if you don't really like the way that looks right now, we can write 0.0001609. So very, very unlikely that I find 150 students whose combined average is above 29. And we tie that back into the context. So I will type that out. So there is a 0.01609% chance. All I did here was move that decimal place. Two over to find the percentage. So there is a less than 1% chance of you finding a sample of 150 people that has a combined average of over 29 points. That the average score of 150 students on the ACT is greater than 29. And we've tied it back into the context. There's a couple different ways that you could have expressed this. If you hadn't felt comfortable putting it back into a percentage, you could have just said there is a 0.0001609 chance. But again, typically when we're bringing it back into the context, that's when we bring it back into percentages. But either way, both of those answers would have been correct. All right, that is the end of that first practice problem.